Hello everyone, my name is Rohan Bhavishi and I'm a PhD candidate at UC Berkeley. In this video, I'll be presenting our work on program synthesis by reasoning over graphs and the resulting tool named Gauss. This work was done with my collaborator Caroline Lemieux, who's now faculty at UBC, and our faculty advisors Kaushik Sen and Ion Stoica at Berkeley. So what is program synthesis? I'm sure many of you are familiar with the term, but let me still describe it for completeness. At a high level, a user provides a synthesis specification to a synthesis engine whose job is to come up with a program in a target language that satisfies the specification. Let's look at the synthesis specification in more detail. One option for the form of specification or specification modality is input-output examples. Since the commercial success of Flashfill in using input-output examples to synthesize string transformation programs in Excel, input-output examples have been used as a specification modality for a number of other domains, such as data extraction, visualizations, and table transformations. In this work, we take a closer look at the use of input-output examples for the domain of table transformations. Just to clarify, the input-output example here is an input and output table, and the target program is a table transformation program in a language such as R or Python. First, we're going to see why input-output examples are not necessarily ideal for the domain of table transformations. Consider the following input-output example. To synthesize a program, the synthesis engine must determine how 102.5 is computed, either via reasoning or by trial and error. 102.5 here is in fact the average of 4 cells in the low and high columns, namely 50, 70, 100, and 190. But this information was already known to the user, otherwise they would be unable to create the example in the first place. Thus, readily available information is lost. From a synthesis engine standpoint, this information loss is critical as it can lead to a loss in performance and an increased chance of producing an undesirable solution overfitted to the example. Now imagine if the input table had many more rows, which is highly likely for a table containing inventory details like this one. In this case, specifying the complete output would defeat the purpose entirely. The only other option is for the user to provide a small artificial example and then adapt the solution for the original input. Thus, providing examples can easily get tedious and hamper productivity of the users and the overall usability of the tool. Now we look at how our tool Gauss tackles these issues. First, Gauss uses a dedicated UI to help the user specify the input-output example. First, the user loads their input table using the UI as shown here. Gauss provides access to a number of primitive operations such as sums and means that can be applied to any arbitrary selection of cells in the input using the UI. In this example, the user selects the 4 cells that need to be averaged and picks the mean operation. The result of the operation is copied to the clipboard. Then the user can paste the result into a cell in the output by simply using Ctrl-V or Command-V. This way, Gauss is now aware of the fact that 102.5 is the mean of the 4 values in the input. But how does Gauss represent this internally? Under the hood, Gauss represents this interaction as a graph. The nodes of the graph correspond to the cells, columns, and rows of the input and output tables, and the edges capture the relationship. In this case, there is a mean edge from the nodes corresponding to the 4 cells being averaged to an intermediate result node, which then has an equality edge to the node corresponding to the cell in which the user pasted the result. This is first of Gauss key's features. It preserves readily available information. Another major feature of Gauss is that the user can now already click synthesize and ask Gauss to synthesize a program. That is, Gauss accepts partial outputs. Gauss promptly comes up with this R program, whose output table is shown over here. Note how the output not only contains the 102.5 cells specified by the user, but has an entry for shirts as well. This ability of Gauss to accept partial output naturally lessens the burden on end users, as they can now focus on providing only the most important elements of the output that are sufficient to describe the transformation. How does Gauss determine if a program should be returned? This leads us to concretely define the synthesis specification for Gauss in the presence of explicit user intent. A program is returned by Gauss if its output contains the partial output specified by the user as a subtable. That is, the values in the partial output are present in the output of the program, as is the case for 102.5 here, and the row and column relationships are also preserved. Additionally, though, the user intent must be consistent with the program's behavior. In this case, the program must compute 102.5 as the mean of the 4 values and not some other operation that happens to lead to the same result. How does Gauss perform this check? This is where the graphs come in. Essentially, Gauss ensures that the user intent graph is a subgraph of the graph abstraction of the program P. What is the graph abstraction of program P? The graph abstraction of P captures its behavior on the given input as a graph. In other words, it relates the input to P to the output of P as a graph, which is shown on the bottom right here. The consistency check is operationalized as a subgraph check between GUser and the graph abstraction of P. As you can see, all the nodes and edges in GUser are indeed contained in the graph abstraction of P. This consistency check ensures a stronger match with the user's intent as opposed to simply checking if the partial output is contained in the program's output. But how do you obtain this graph abstraction? In the interest of time, we request you to refer to the paper to get more details on this process. But for this talk, all you need to understand is that the graph abstraction of a program captures its behavior for a specific input as a graph. Next, we will see how Gauss uses graphs to speed up the search for a solution program. To recap the motivating example and the spec, the user provides an input table and a partial output using Gauss's UI, which captures the interaction as a graph. The goal is to find a program such that its output is contained in the partial output as a subtable, and the graph abstraction contains GUser as a subgraph. Given the user spec, Gauss employs a two-tiered enumerative search to find the solution program. First, Gauss enumerates what we call skeletons. A skeleton is essentially a program without arguments. Now, for simplicity, assume that there are only two available functions in Gauss's transformation language, gather and group by, and the maximum number of function calls in a program is 2. Then there are 6 possible skeletons as shown here. The first to contain a single function call, while for the others, the second call consumes the result of the first. Then Gauss considers each skeleton one by one and enumerates programs that can be obtained from the skeleton by filling in the arguments. For example, for the first skeleton containing a single call to group by, the possibilities for arguments are shown on the right. This set of programs is denoted by programs of sigma. Gauss first tries to reason at the level of skeletons. It performs reasoning to eliminate skeletons which are guaranteed to not lead to a solution. That is, no matter what argument combinations we choose, the enumerated programs for this skeleton will not satisfy the user specification. How does Gauss check this? Without enumerating any programs for a skeleton sigma, Gauss tries to prove that GUser will not be a subgraph of the graph abstraction of any program in programs of sigma. Clearly, if this is true, then all the programs will fail to satisfy the spec, and therefore we call such a skeleton sigma infeasible. In the case of the running example, Gauss can indeed prove infeasibility for sigma 2 and sigma 3. Why? Essentially, Gauss infers that gather by itself cannot perform aggregation, and hence the graph abstraction will never contain a mean edge as is present in GUser. How does Gauss prove this? It uses a combination of reasoning at the level of graphs and properties of the functions in its transformation language to prove this. But again, in the interest of time, we request you to refer to the paper for more details. Once Gauss has eliminated the infeasible skeletons, it goes ahead and enumerates programs for each skeleton one by one. It checks the enumerated programs against the spec and learns from failures to search even faster. Let us see how Gauss does this. Suppose Gauss picks the first skeleton sigma 1 to explore, which contains a single call to group by. Gauss enumerates the possible programs by trying out various argument combinations and finds that none of them satisfies the spec. Gauss tries to find a small concise reason that explains the failure of all programs. In this case, it finds that this particular subgraph of GUs are highlighted in orange, representing the fact that two cells in the same row are being aggregated together, is not present in the graph abstraction of any of the programs explored. Why is this the case? This is because group by in the group by function in Gauss's transformation language can only aggregate across a single column, not multiple columns. We call this graph a conflict graph, and Gauss keeps track of this for the remaining skeletons. The next skeleton explored by Gauss is sigma 4, involving a call to group by first, whose result is then fed to gather. Before enumerating any programs, Gauss checks if the skeleton is guaranteed to run into the same issue as the previous one by utilizing the conflict graph that was identified. In fact, Gauss is able to prove that if there was a program in programs of sigma 4 whose graph abstraction contained the conflict graph as a subgraph, then this graph over here would also be a subgraph of its graph abstraction. Well, what does this mean? Let us unpack this. This means that the cells that are being aggregated belong to the same column. But this implies that we run into the same issue because we know from guser that these two cells are indeed in different columns. Thus, Gauss is able to move on without explicitly enumerating any programs, saving precious synthesis time. For more details on how Gauss arrived at this conclusion, we again request you to refer to the paper. With the next skeleton, however, Gauss encounters no such conflict and is able to return the solution program, as shown here. We now present an evaluation of Gauss along two main dimensions. The first involves measuring the additional pruning power that comes from graph-based reasoning. Specifically, we compare Gauss, which receives the input table, the complete output table, and the complete user intent graph, against state-of-the-art reasoning-based synthesis systems that accept only input-output examples, namely Weiser, Morpheus, and Neo. Since the space of transformations supported by each of the tools differs slightly, we compare against them on an individual basis based on their respective benchmarks. Since the benchmarks only contain the output table and do not come with a graph, we generate the graphs automatically by taking the graph abstraction of the ground truth program. Overall, in this experiment, we expect Gauss to be faster than the other tools and search fewer programs because of the additional graph information that is available. First, we look at the synthesis times. There are three graphs, one for each tool. The x-axis is the time taken by Gauss, and the y-axis is the time taken by the tool being compared against. The dots correspond to individual benchmarks, and dots above the gray-black line indicate that Gauss is faster than the respective tool, and those above the green dashed line indicate that Gauss is more than 10 times faster than the tool being compared against. On average, we find that Gauss is 7x, 26x, and 7x faster than Morpheus, Weiser, and Neo respectively, and this is solely because of the additional pruning power that is coming from Gauss and the additional graph information that is present in the spec. Next, we look at the number of programs explored before arriving at the solution. The graphs are the same as before, only they represent the number of programs explored instead of time. A lot of the dots are above the green line, indicating that Gauss explores more than an order of magnitude less programs than the tools being compared against. On average, we find that Gauss explores more than 2 orders of magnitude fewer programs than the other tools, thus indicating the pruning power of Gauss based on the additional graph information. Next, we measure the potential benefits of the ability of Gauss to accept partial outputs. Specifically, we measure the size of the smallest partial output that can be provided to Gauss while still obtaining the right solution. So we, the experts, manually come up with the smallest partial output on which Gauss returns the correct solution. For this experiment, we only use the benchmarks from Weiser because they were also used in the context of partial outputs in their respective paper. And these benchmarks consist of real-world tables, which are not necessarily artificially reduced for the purpose of synthesis, thus reflecting a more real-world scenario for Gauss. The results are again visualized as a scatter plot, with the x-axis being the size of the partial output and y-axis being the size of the original input. Most of the dots are above the green line, as you can see, indicating a reduction of more than 10x, and a number of dots are above the gray line, indicating more than 100x reduction. On average, we found that a 33 times smaller partial output could be provided to Gauss while still obtaining the right solution. This indicates that Gauss has potential for greatly reducing the burden on end users when it comes to providing a synthesis specification. In summary, we highlighted how input-output examples can be problematic as a specification modality for the domain of table transformations. We showed how Gauss employs a dedicated UI and uses graphs to capture precise, readily available relationships between the input and output. We demonstrated how Gauss uses graphs for speeding up its search by pruning away large parts of the search space and by using inductive reasoning to do so. And lastly, our evaluation suggests that graph-based reasoning has the potential to greatly improve synthesis times and reduce the size of the specifications required from end users. Thank you very much for watching.